Good morning, everyone. Thank you for joining us today for the Introduction to Compressed Air Systems webinar. My name is Beth, and I'll be your host this morning. We'd like to start off with a safety moment. Safety is a core value at PGE, and we want to remind you to be safe around electricity. As you consider installing or retrofitting new equipment, please keep safety in mind. We would also like to encourage your family and staff to be prepared with an outage kit, and you can visit our website for more safety information. We would also like to thank the Energy Trust of Oregon and the Northwest Energy Efficiency Alliance for their support in co-sponsoring this series of free energy efficiency trainings that are open to all Northwest utilities and their customers. Before I introduce this morning's presenter, I'd like to show you some tools you'll be using during the webinar. To the right of your screen, you'll see several windows: the chat window and the polling window, which will appear at the end of the session. If you have any questions during the webinar, you can submit them to me, the host, through chat, and I will ask the presenter these questions at the end of the webinar. And now at the top left corner of your screen, beneath the Quick Start tab, you'll see the following tools, which I will circle here: an arrow tool, a text tool, and a marker, and the presenter will ask you to use these during specific slides during the webinar. And now I'd like to introduce this morning's presenter, Eric Bessie. Eric is an Oregon licensed professional engineer with over 17 years of experience in the compressed air field. He is a compressed air system audit leader, control specialist, project manager, and has extensive experience with rotary screw, centrifugal, and reciprocating compressors. As a sole proprietor, Eric developed AirMaster Plus, a nationally recognized software tool used to model existing and improved compressed air systems. He provides compressed air training courses across the country and is a certified Compressed Air Challenge Level 1 and AirMaster Plus Specialist Instructor. And now I would like to hand the presentation over to Eric. Eric?
Hi, good morning, everyone. Let's see, I think this is about the fourth one we've done, and these keep getting better and better, I believe, anyway. And I'm glad everybody could attend today. And it's kind of an exciting topic. Compressed air, it's something that I never would have thought would have been such a big deal, but about 1993, thereabouts, the Bonneville Power Administration conducted a study and discovered that in addition to lights and insulation and windows and all that kind of stuff, that compressed air was a big piece of the pie when it came to industrial energy. And not only that, but there happens to be a pretty good opportunity to improve it. So let's take a look at what we have today. That's my name, that's my arrow. So as we go along, by the way, like we said, we be using some of these tools. So as an example, this arrow tool here, I just click here and I can point my arrow. So that's that. Okay, today's agenda. Well, what are we going to do today? Well, first of all, why should we even care about compressed air? So I'm going to go over some of the concepts of what goes into making compressed air and how we use it, because we kind of take it for granted, really. Most people do anyway in their plants. Different types of controls. The actual system pressure, that's the pressure that's inside the pipes. And then, of course, talk about leak reduction, which seems obvious, but I think there's a little more to it than just fixing your leaks, and we'll see what other kind of problems leaks can actually create. All right. So first of all, I'd like to know who you are. I'd like to know what kind of role do you play. Are you a facilities manager? Are you an end user? What kind of person are you relative to your plant? That'll help me understand who you are. So up in the upper left, click your pointer or whatever. Yeah, there we go. Just put some blotches on there. Got some consultant, facilities manager, and let's see, myself, I'm more of a kind of a consultant kind of guy, and that's who I am for you today. I don't represent any products or anything like that. I'm purely here to help kind of get your feet wet in this stuff. And by the way, there's another class coming up on the 30th of this month. There's a half-day class that you can meet me in person if you want. Maybe I'll ask for your autographs, or I can try to sell mine. At any rate, I see we have good deal. A lot of consultants, excellent. And a facilities manager. You know, facilities manager, number one thing is keep the plant running. And whatever we do with compressed air to try to make it better, if it causes us headaches on production, then we've not done ourselves a good service. So we always keep that in mind. That's actually paramount. keeping the plant running. Okay, excellent. All right. Well, let's move along. Possible myths about compressed air, and they were myths to me when I first came into this field and started studying at Oregon State University, and really getting kind of my head into this stuff and understanding what it's costing us, because it's certainly not free. Another myth that people tend to think is that more pressure is better, and sure, why not? It's kind of a Texan attitude. Bigger is better, more is better, and we'll see the impacts both in your wallet and actually on a maintenance standpoint can actually kind of hit you there too with too much pressure. Our system operates at 100 psi. That's just kind of the mythical value that all plants need 100 psi, when in reality it's all over the board about what you actually need. And not only that, but what's your system actually operating at? I always ask this question when I go into a plant, and I'll get a variety of answers, but a lot of times I'll just simply get 100 psi. Why? Because that's what's stamped on the side of the compressor, but that doesn't mean that that's what it's operating at. All right. Okay, number one on the agenda, why care about air? Take a look at this. This is astounding. About 76% of the total cost of the compressor over 10 years, a life cycle, is due to electricity. Only about 12% of it is upfront cost of the actual purchase of the equipment and installation, and about another 12% for maintenance costs, changing the oil, the filters, making repairs and things like that. That's just typical maintenance. That wouldn't be for a compressor rebuild if it were to crash or something like that. But if we take into account how much energy the compressor actually uses, 100 horsepower compressor, $30,000 a year based on 6,000 hours at 7 cents. That's amazing. 6,000 hours, and that's just a 24-hour, 5-day a week with weekends off. So your plant may actually operate more towards an 8760 or an 8400 hours per year if you operate on the weekends. $30,000 over the first year. The cost of a new, just a regular kind of a plain Jane compressor, 100 horsepower compressor, is going to be about $35,000 to $40,000. So in the first year alone, you've almost paid for that compressor. So that sort of gives you an idea about why that's such a big impact on our total cost over a 10-year lifespan. Okay. Keep your questions in mind too. There's going to be some polling questions at the end. You'll have an opportunity to submit questions, and then I'll address them. So anytime throughout this presentation, if there's something that you don't understand or you want further clarification, or if you have a comment and say, hey, Eric, you're wrong here because I'm not always right, you let me know. Hopefully I'm right just about on anything with this because I've been doing it for a long time, but keep your questions and comments. Application. Okay, let's say that we have a load we want to lift up, with a winch. And let's say with the winch, we're going to use a 1 horsepower motor with a pulley to lift whatever it is I'm lifting. So maybe there's a weight down here, something like that. And I can do it either directly with an electric motor or with an air motor. So with the air motor, of course, I have to pay to compress the air and then feed it to the motor. Whereas with the motor, it's direct. It's right from the electricity to the motor to the shaft. Take a look at that. $200 per year for the electric motor versus $1,500 a year for the air motor. That's assuming the same operating hours, the same electrical rates for everything. It's about 7.5 times the cost to operate an air motor versus just a direct electric motor. And I think what you're thinking, and hopefully you're thinking this, is that the obvious thing is that you have to pay the compressed air. So first of all, you're paying to compress the air, then you're using it. So there's sort of this middleman called compressing the air. And why is it so darn inefficient? Well, we'll take a look at that. But first of all, I'd like to take a polling question and talk about controls. So using your tools, go ahead and click your arrow, whatever other means you want to do, and see if you can pick what type of controls you think your in general your compressors have. And you may not know, and if you don't know, that's perfectly okay. I don't know because I don't have a compressor, so I haven't bought it yet. But you may pick, okay, we've got a variable speed, variable frequency drive. Excellent, okay. So, and some of you consultants may not have, compressors because you're consultants. You don't actually run in a plant. And a StartStop, okay. Good for small compressors. We'll talk about each of these control types a little more. The most common one that had with rotary screw compressors that had been prevalent throughout, the 60s, 70s, and 80s until we started caring about it was this guy right here. That was the most popular, modulation. We'll talk about that. And I'll talk about why it's so inefficient, as you'll see. Okay. Let's talk a little bit about the different type of controls. Start, stop. Okay, so this is like your little pancake compressor, or if you're a construction person and you're putting someone's hardwood floor in, you have this compressor sitting on the floor, and it starts and it runs and it pumps up to a pressure set point, and then it just simply shuts off. And then it waits until you use compressed air, so you use a few nails and it drops the pressure down, then it starts back up. Or this is just like a service station for your tire, just a start-stop. They're really only good for small motors, smaller types of motors, because starting and stopping a motor is hard on the motor in and of itself, and particularly with big motors, they develop a lot of heat. So you maintenance guys out there that I saw, you won't want to start and stop a 100 horsepower motor very often at all. So it's really only suitable for small motors. And then the most common one, or today it's very common, I won't say it's the most common today, but it was up until the early 90s, was just straight inlet modulation. Inlet throttling is simply restricting the air inlet to limit the amount of air that flows through the machine. It's just like your throttle on your car. So if you imagine a butterfly valve on the inlet of your car as you operate the gas pedal, it opens and closes. That's exactly what happens with inlet modulation. And it creates a vacuum at the inlet, and that's how it restricts it. Another way to do it would be to stuff a sock down it or put your hand over the inlet. It's all the same stuff. It's called throttling. Load unload. Load unload is kind of like start stop, except that instead of shutting off the motor when we get to a higher pressure set point, it simply unloads. And what I mean by unloading is it's kind of like you're at a stop sign, stoplight with your car. You put it in neutral, got the clutch in, or your transmission's in neutral, and it's just idling. It's not really doing any work. All it's doing is idling, using enough power to keep the motor turning, but you're not actually putting horsepower to the wheels. So that's kind of like what load unload is. So it actually allows it to drop down to a very low power, but not completely off. Variable displacement. That's kind of a funny term, but you could imagine your car engine. So let's say you have a 4-cylinder engine, and if you were to disconnect the spark plug on one of them, or simply not give one of the cylinders fuel, you would now be operating 3/4 of what the full displacement was, 3 out of the 4 cylinders. So you varied the displacement. Not all 4 are working, and reciprocating compressors are kind of like that. And rotary screw machines don't have pistons, but they actually have a way of adjusting the length of the rotor. We can talk about that a little more on October 30th, but just imagine a compressor that's able to vary its displacement. And I'll show you a curve and how that performs. Okay, and I definitely saw a few people have these variable frequency drive. More generically, we call them variable speed drive because there are some DC motors out there that don't function on variable frequency, but variable voltage and current. So, but they accomplish the same thing, and that is they adjust the speed. So that's simply it. And that's kind of like your car engine. It's speed up, slow down. So the tachometer on your car is just like the variable speed on an air compressor. You could look at the speed of it. Very well suited for trim duty. And we'll definitely talk about that. I'll talk about what trim duty really means. Okay. A little bit more on modulation. So modulation is, if we look at, pretend like this is the air inlet. This is a butterfly valve. When it's wide open, we get as much air as we can through the machine. As pressure in the system builds, I know that I need less and less air because I'm not taking out as much as I'm putting in, so I can start to partially throttle the compressed air. And we call that part load or part loading of the compressor. and less air goes through the machine. So it's just like your car throttle. You can just imagine your gas pedal. In real life, we can take a look at this. Our air is entering through a filter. There's a filter up here. It goes through a throttle body, and right here is a shaft with that butterfly valve that I'm talking about, that I've been talking about. So it just moves back and forth, and if, for all you mechanics out there, you just look, there's just direct linkage, just like your carburetor linkage, right? Yeah, everybody has carburetors nowadays. Well, your lawnmower still does. So anyway, so back and forth goes this rod. It's connected to another, we can call this a doohickey, but inside the doohickey is a diaphragm. It's an air diaphragm, and air pressure from downstream of the compressor or the oil sump, somewhere where it gets system pressure, feeds it, and it just simply moves this thing back and forth, and there you go. So it's kind of like a cheap cruise control on your car. You know, it automatically adjusts the amount of flow to balance out the pressure downstream to keep the system full but not overfull. All right. So that's inlet throttle, and that's a really easy, simple one to understand. Let's take a look at what a performance curve looks like for an inlet throttling machine. Down here along this axis, if I'm allowed to use that word, we don't want to get too technical. But I have airflow, so 100% airflow is here. And then as I need less and less airflow down to 0, I'm interested to know what the compressor power does. And so over here we have power. Average power, percent of full load. So at 100% flow, I have 100% power. Well, that makes sense. It's just wide open. And then as I diminish or reduce the amount of flow through the compressor, notice that the power drops, but it doesn't drop very much. I mean, holy smokes, look at this, 50% flow. I only need half the flow through the compressor, and I'm still using a whopping 82% power. I mean, that's just, you can see right there, it's just not a good deal. And it's kind of like driving down the road in your car. You have your foot mashed on the gas, and you're using your brake to throttle the car. So you apply brake to slow down the car rather than letting off on the throttle. It's kind of like that. A loose analogy. Okay, so that's inlet throttling. Now, the best we can do is what's called start-stop. But as we mentioned, it's not particularly good for large motors. But this sort of makes sense. 100%, you're running 100% power. And then once I shut the compressor off because I built up pressure, it's off. So it just sort of bounces along. You know, it turns on, then it turns off. It turns on, then it turns off. And you can imagine the weighted time of being on versus being off, and then I could actually have a varying average flow that's coming out of the compressor, average. Okay, load unload. Remember, we talked about load unload and how that is pretty close to start-stop in a sense. It behaves similarly in that it's either making all flow or it's making no flow, and then it sort of just loads and then loads, loads and then loads, just like we talked about with the start-stop. So it gives you an average flow and an average power, depending on how long it stayed loaded versus unloaded. And you can see, like at 50%, it's quite a bit better than modulation, but it's not quite as good as start-stop. But it's a happy medium. And I also have this word called ideal. There's something called cycle losses that are related to the oil sump blowing down and then having to fill back up. And we can get more into that into detail in the 30th, on October 30th. But this is an ideal curve. And what really happens in reality is we get a curve more like this. It's not really ideal, but it has to do with the amount of air receiver capacity that I have. So, you know, maybe I have a 2,000-gallon tank and I have a 1,000 CFM compressor, and that's what that is. I'll just say that the more air receiver you have, the tendency of this curve is to start to approach or get better, improve, and get closer to this ideal. More on that in the 30th. Now here's kind of a hybrid curve. It combines inlet modulation, so it's a solid throttling line, and then in this particular example, once it gets to 80%, then it blows down and unloads. And so we get kind of a combination between inlet throttling and load unload. And these are still common. This is a common way to go. It's just, hybrid sort of control that's out there. They can get out of adjustment really easily, and they're kind of finicky and require attention and maintenance. Nothing really difficult. Again, this isn't rocket science. These are just, simply understood components, but they can get out of adjustment really easily. At last. Okay. We're in the new age where variable frequency drives are the best thing since sliced bread, and we put them all over the place and on everything. Everything needs a VFD, right? And you look at this, and boy, this curve is darn good. It approaches a start-stop. I mean, it's not much off that. But I'd like you to pay attention to the shape of the curve, and if you follow it, what do I see right up here? I see that at 100% flow, I actually use about 103% of power. It's worse than all the other ones. And the reason why is because the variable frequency drive unit in and of itself is really just a heater. There's inefficiencies associated with just the drive unit. But then I'd argue, why would you buy a variable speed or variable frequency drive compressor if all you're going to do is run it base loaded or at full load? There's kind of defeats the purpose of purchasing it in the first place. Which leads down the path of, gosh, should I put VFDs on all my compressors or maybe just one or two of them? Because some compressors are going to be base loaded. So we can start to talk about system design a little bit. But these are pretty representative curves for the different types of controls that you can have on a compressor. Lubricant injected rotary screw, the most common compressor out there. We used to call it oil flooded. It's another term that's used for that. So, where does the opportunity lie? It really lies in the part load performance of these compressors. Those were all those curves that I just showed you on the previous slide. In every system, at least one compressor will operate at part load. At least one does. Something has to have slack. If your plant required 1,000 CFM of compressed air at all times, never varying, you could purchase a compressor that exactly matched that load, and it would run at full load, and there would be no part load. But that's just simply not the case. Leaks come and go. Production varies. People go to lunch, and the plant goes down. There's all these kinds of different things. So we know that the actual demand of the plant varies. So somebody has to vary. One of the compressors has to vary. And if we do so, we want to make sure that it's the most efficient way that we can and reliable. That's another key word, reliable. Must keep the plant running. Inlet modulation should be avoided. It's just a very inefficient way to go. It used to be the simple, easiest thing to do in the past, and it was, but it's become very, very expensive way to operate. So consider load, unload, or VFD control for the trim compressor. Very, very important. Load, unload, in particular load, unload, must have adequate storage. All compressed air systems should have a degree of storage, but particularly with load, unload controls, we really want to make sure that we have enough so the compressor doesn't short cycle. More on the 30th. All right. Okay, so what kind of opportunity do we have? Let's say that we have an average load of 250 CFM. I have a 100 horsepower compressor. So a 100 horsepower compressor with a demand of 250 is right about 50%. So 250 out of a 500 CFM compressor. And if I measured the power on that compressor, it would require about 72 kilowatts. This is very, very typical. Now, in reality, of course, the demand really swings, right? Sometimes it's high during peak production, and then we go to lunch and the demand's down here. So it's varying, but let's just say on average it's 250. Let's compare this to a variable frequency drive compressor. All I did was take those curves that I showed you on the couple slides ago with all those part load performance curves. It's not rocket science. I just took the flow and I plopped it right down on the curve. And you can see that there's a pretty impressive savings of 31 kilowatts, which is about $13,000 a year. based on our 6,000 operating hours and at 7 cents. So this is real stuff. It's not made up. This is a very common example. So you look at that and you go, wow, okay, should I go out and buy a brand new compressor? Well, if your compressor is in very, very good shape and it's brand new, maybe you could retrofit it instead of just buying a new compressor. You'd want to work with your service provider, your compressed air distributor, make sure that that's okay. But in a lot of cases, you can actually retrofit a compressor with a drive and achieve this performance or close to it. So consider that. But you can see the numbers. I mean, that really kind of drives the point. Okay, we've talked about controls, and then I promised to talk about pressure, and here we are. So grab your tool of choice and let me know what you think your compressor operates at. I'm going to go back to my old days when I didn't understand anything, and I have my system jacked up at over 120. Do I need that? I don't know, but that's where it's operating at. I walked up to the compressor air system gauges, the gauges on the compressors out in the air receivers or wherever in the plant, and it's running up at 120. Now maybe I really need it, but that's not the point. The point is, do I know what it is? And some people don't know, and I can see that. Yeah, and there's a good answer. 100 to 120, very, very typical. Okay, what does pressure mean to you, and what does it mean to your wallet? Let's take a look at that. Rule of thumb, and like all rules of thumb, there's always exceptions. These are just, rules of thumb. But as a rule of thumb, for every PSI reduction in pressure, I can save about 0.5% of power. So a 10 PSI reduction is going to be about 5% savings, or $1,500 a year in our kind of examples we've been using so far. And it's kind of just like, hey, when you're a kid and you're pumping up your bicycle tire, the more pressure that was put into the more air that was put into the tire and the pressure increase, it becomes harder and harder to pump up the tire. And that's the same thing. It's very simple that way. It's just resistance back. But not only does it cost more energy to pump up to a higher pressure, there's something called artificial demand, which is really the amount of air that your system uses in excess of what you really need, solely because you have increased your pressure beyond what you really need. And I'll explain that a little bit, but suffice to say that for every PSI reduction, I can reduce this amount of demand by about 1%. And it's kind of like your tire. So you go up to your neighbor who you've been arguing with over time, and he just doesn't see it your way, and you say, well, I'm going to let the air out of your tires. And at first you push in the little air valve, Schrader valve, and you push that in, and it hisses like crazy at first. And then as the air depletes from the tire, the hissing sound gets less and less. Your compressed air system is a big tire. You can think of it like that. So it uses more air as pressure is increased. And not only that, but things like cylinders, well, the higher the pressure, the more little molecules, the little marbles of air that you can shove into the cylinder, and that's more air. So you're using more air. So take that into consideration. Rule of thumb. So sources of pressure drop. Now, let's say that I want to take my system that I have at 120, and I'd like to drop it down to 100, but I can't because I have restrictions in the line that are keeping me hostage to a higher pressure. So we have things like, oh, here's a good one, multiple filters in series. Filters impose, in addition to cleaning air, they impose a pressure drop, right? So you have to pay for that. So that means if I need 100 PSI downstream, I have to operate my air compressor at a higher pressure to overcome that pressure drop. And then all of a sudden my meter starts spinning faster and my wallet gets a little lighter. Here's a good one, distribution system not looped. The more ways you can allow the air to travel to get to your end uses, the better you are. And that relates to this next one. Even leaks can contribute. Look at this. Higher flow increases the air velocity in the pipe. The higher the air velocity, so you can imagine, in addition to the air that has to travel down the pipe to feed the end use, you also have to have air travel down the pipe to feed the leaks that you have. So it's going to be increased velocity. And so you can imagine the freeways. In the freeways, the more cars that enter the freeway that try to go down the freeway, eventually you have a traffic jam, and it's caused in the air system. It's caused by friction on the pipe. So if we can reduce the leaks, we can reduce the velocity, therefore decreasing the pressure drop, which helps me out. So that's part of the kind of the double-edged sword of leaks. Not only are you leaking, but it contributes to pressure drop. Okay. Think about this. Think about other situations that you might have in your plant that might be contributing to pressure drops, which hold you hostage to a higher pressure than really needed, and it's costing you. Okay. Here's another artistic opportunity for you. Take a look at this. Grab your tools. Let's see, dark colors work well. So if I pick a highlighter, pick a dark color, circle or mark anything that you find interesting on this slide that might be contributing to a problem, or it could be a good thing, depending on your perspective. What do we see here? These guys right here are filters. 1, 2, 3. I have 3 filters. Well, if 1 is good, 3 are better, right? Why not? Clean the air, clean the air. I also noticed something else. Somebody circled a valve. Very, very astute. We'll go over that. That's actually a key part of this whole thing. This really tells a story, this whole thing. First of all, look at this. Look at this pipe. What do we have on the outside of the pipe? Dust. We're actually in a sawmill. And if you look around, you could probably say to yourself, this is probably not as clean as my bedroom is. Maybe it compares to my bedroom when I was a little kid, but there's just a lot of dirt and stuff all around. And oil collects dust. Dust blocks up here. This is actually a radiator fan with cooling fins. So it contributes to potential overheating because just like bugs that hit your radiator when you're driving down the road, the more dust that gets on the fins, the less cooling can happen. So pretty soon we've compromised our compressed air system, and maybe some moisture is getting down the line because I can't cool it to remove the moisture, and we put more filters in, and then the filters get neglected. I mean, it's all about neglect, right? I mean, this room is not a clean room, and not neglect in the sense of a neglectful person, but just that time and resources are limited, and we just can't do it. So anyway, the filters were installed. The filters began to plug because they weren't changed enough. Pretty soon, this bypass valve, which somebody, astute observer, noticed, it's cracked open, bypassing the filters because I couldn't get the air down the pipeline to the end uses. So now we're not even filtering. So there's some pressure drop there, and we're not filtering. So we have dirty air with a high pressure drop, and our operating costs have really gone up. Okay. What about here? Take a look at that and mark anything that you think might be interesting. Might be a problem. I certainly see something that was a kind of a, what I call kind of a quick fix, an emergency fix. So yeah, we've got looks like we have maybe a 3/8 or 1/4 inch, whatever size of pipe that is, or rubber hose rather, all for the purpose of getting the air from here over to here. And that's our highway. So we have a little back alley, and we're trying to get rush hour through there, and it's just not working. Disconnects here can be restrictive, and if you buy the cheap ones, they're restrictive, and they eventually leak, and it's just not the best fix. And what that's doing is it's starving the downstream side from air pressure, thereby commanding or requiring that we jack up the pressure on the supply side, and it hits my wallet, 0.5% per PSI, right there, all because of that cheap, got to have it now fix. It's it's a duct tape baling wire type of fix, really. Should put a nice piece of 1-inch pipe in there, would be better. Okay, what about here? Take a look. And again, this is a situation of I have to have it now. What can I do? I'm in a pinch. I've installed this table saw over here, okay, or chop saw. It looks like chop saw. I've got a foot pedal operator. Plug it in. So this is just like Christmas time when you plug in, your Griswold, and you plug in all your lights, Christmas vacation time. Plug everything into one socket. It's actually, pneumatic-wise, it's exactly the same as what happens when you try to plug too many things into your electric circuit. There's too much current. Electrical current is like a flow. The more flow you have, the more resistance or pressure drops. The same exact thing. And there we go. And always put your tools back. Learned that from my dad the hard way. All right. Leaks. Polling question. Yay, polling. How many leaks do you have? I feel kind of leaky. There we go. I got lots of leaks. Yeah, a couple of I don't knows. Yeah, how the heck do you know? I mean, I'll tell you what's typical. Really what's typical is right in here is a real typical value for a plant, and that's just like kind of like normal. It's kind of like quote unquote acceptable, except well, we finally got to the point where we're not accepting Congress, but you kind of live with garbage for a long time, and you sort of say, okay, this is acceptable, but really 20 or 30%, that's a lot of leaks. So I would encourage you to just go into your plant on a downtime or maybe a kind of more of a quiet time if you have that opportunity, or even on the weekend and fire up the compressors and walk around and listen. Of a total plant demand, typical components of demand, only about half of the airflow actually goes to what I would call normal production or what's actually required by production. Yeah, half of the air you put goes towards that. About 10% of it, roughly, goes to this artificial demand thing. Remember, systems leak more when they're pumped up higher than what I needed. And this is just a typical thing. Your plant's going to vary, but it's just to give you a real typical idea. It can happen. There's my 30% leaks I talked about. And then there's some things I call ideal uses. Bob over here is really hot, and he's got an air one. He shoves it down his shoe because he's sweating like Dickens. So I'm using compressed air to keep myself cool. Or maybe I'm using compressed air to blow off parts during production when really a blower might suffice. So we can talk about different ways we could use air. But first, let's get a real perspective on leaks here. Look at this, a 16th-inch hole. And that's about the size of a hole if you had a regulator. You know how regulators work. They're basically just a balancing act between the diaphragm, the upstream, the downstream pressure. And it has to have a bleed hole to relieve so that the thing can open up when you need more air. Well, it just constantly leaks. In a 16th-inch hole, that's not too uncommon. $720 for that regulator just to be there. I mean, that adds up, and you can imagine all the little regulators you have. Now, there's not much you can do about the requirement of a regulator. I mean, if you truly need it, you have to have it, and there it is. But boy, doesn't that put into perspective about what leaks can do? Leaky packings, pipe fitting threads, blown diaphragms, hoses that forklift operators like to drive over. And there you go. So $100 leak in a system cannot probably can't hear or feel it. I mean, it's just there, but you wouldn't know about it unless you had a special tool like well, I guess soapy water would work, or an ultrasonic leak detector, which is a good way to find leaks, potentially, if you buy a good one, if you know how to use it. But finally, when we get to about a $500 leak, I can start to feel it, and then finally I can feel and hear it. So you walk by, you hear this hissing, and your shirt tails is flying in the wind. So there you go. What this means is that leaks are actually not hard to find. You can find a $800 a year leak. Before you know it, you can save thousands of dollars a year by fixing your leaks, and they're not hard to find. Leaks can be tagged, but please go fix them after you do. I mean, it's easy to find the leak, but you have to actually fix the leak. And also, as soon as you fix a leak over here, another one crops up over here. It's kind of like balloon art. When you squeeze the balloon, I've diminished it over here, but then it just squirts out somewhere else. I mean, you just have them all the time. They're like weeds. They'll come back. Common leak areas: pipe joints, air hoses, worn packings. Here's a good one: open condensate traps and shutoff valves. Okay, so maybe on the bottom of your air tank, there was once upon a time a nice either a time drainer or a float type, no air loss drain. but maintenance dollars are a little thin, and so that device got neglected, and pretty soon it plugged up. Either it's stuck open or it's stuck closed. And if it's stuck closed, then maybe you walked by and you said, well, I'm just going to open up this little ball valve and crack it open. It doesn't take long for the moisture to evacuate. After that, it's all air. It's all that expensive air that, $30,000 a year to generate compressed air for about 500 CFM or 100 horsepower. So that's expensive. And if you think about that, that's 500 CFM. You go back to your leak table and you can see it doesn't take much to do that. So it's really expensive stuff, and there's something we can do about it. What about here? Okay, mark where you see an issue. Yep, right there, right? See, I do a pretty good job for you guys because I put all the things right in the middle. I put the elephant right in the middle of the room for you, so you don't have to look for it. Excellent. Yeah, duct tape. Duct tape is neither particularly effective nor is it safe. Something safety that I forgot to mention, by the way, if you're working with compressed air and you're in the compressor room, please wear safety goggles because stuff can fly around with air. Wood chips can hit you. And plus, the compressors themselves are extremely noisy. And you may not notice it, but if you're in a room for a couple hours, you'll have fatigue. It's just like being at a rock concert. And eventually it'll damage your hearing. So wear ear protection. Here's a little valve to open and close to turn on, off the air, on and off. And so, I mean, it's off. That's good. You can probably imagine what size of nozzle. I mean, that looks at least ½ inch. That's probably 3/4 inch. Looks like that's probably a 1 inch bush down to a 3/4. And a lot of air can go through a 3/4. If you revert back to that screen before the leaks, an 1/8 inch leak, and if you have a 3/4, gosh, that's a lot of air. Of course, it's fun to blow stuff around. We'll talk about that. Okay, what about here? You don't need to circle it. I'll circle it. But what I have here is good old-fashioned radiator hose clamp. And they work like a charm for a while. And after a while, just like it did in your old cars, nowadays they don't really use those hose clamps anymore, but if you have an older car that does, eventually the sharp edges work their way into the rubber, and eventually you have an aneurysm and eventually a leak. So they don't work particularly well. What you should do is install those crimped on type of clamps that have the rounded edges that won't dig into the pipe. A little more expensive, takes a little more to install, but you won't have a leak. And I think by now, hopefully you've seen that a little prevention and money up front will save me lots of money down the road in terms of leaks especially. Okay, what do we got next here? Aha. Open blowing. This is a good topic, one of our favorite topics, and it's used for cleanup. And I worked at a plywood mill for a few summers in college, and it wasn't compressed air I used. It was water from the fire hydrant, or from the mill pond actually, that we pump it, and to keep the dust down because the neighbors were complaining about the dust in the lot. So I spent I don't know, a week one time just hosing down the whole thing, which was really an exercise in futility. Same thing with compressed air. When you blow particles around, I mean, could you imagine using a blower in your house to clean up your kitchen? I mean, it's just a tornado, and it's clean right where you blew it, but then the stuff goes over into another corner. Well, it's still there, so now you go to that other corner and blow, and all you end up doing is just blowing stuff around. You're not really removing the material. You're just blowing it around. But I can understand. It's kind of a quick fix. So there we go. It's like about a ½ inch, and, lots of horsepower worth of air going through that guy when he's being used. Oh, look at this. This looks like one of those maybe crimped on type of connectors. That's actually a good thing right there. So out of all this, at least I see a good connection piece. That does not look like a radiator clamp. First time I've noticed that. Okay. Use a broom. In the mill, it was, if you've got time to lean, you've got time to clean. So when the dry chain is down, or the green chain, or planer chain, whatever it is, when it's down, grab a broom. And this gentleman here is probably pushing this stuff off into a collection bin of some sort where we can actually remove the material instead of just blowing it around. And then once we put it into a collection bin, then it can be sold or burned for hog fuel or something like that. So there's a real benefit here as compared to just blowing it around. Plus he's getting good exercise. All right. That kind of concludes kind of the basics. And I really encourage you to attend the October 30th class because we're going to get a lot more in detail about these things. And then you can even carry your education beyond that. But the good half-day class, we'll go over each one of these in much more detail. Part load. At least one compressor has to part load. I hope you agree with that. If not, we can talk about it. But suffice to say that if it does, variable speed drive is perhaps the best option. It's not always the best option, but just about all the time it is. Great savings can be had. Remember, inlet modulation is the poorest way to go. Pressure. Lower is better, and I mean lower is better from an economic standpoint. Production-wise, if you need a certain amount of air pressure to keep the plant running, that's where you're going to operate at. I'm not suggesting that you lower the pressure beyond what you need. But if you could just drop that pressure down by a PSI per week and then start to notice if anything in the plant starts to, if we have any quality issues or anything like that, then dial it back in. But that's really a good way to see right where your plant needs. And then maybe add 5 PSI on top of that for safety. But for every PSI reduction, I could save 0.5% of energy. Not only that, but maintenance can drop too. The less pressure that I'm slamming cylinders with, the less wear and tear on those. And then also, leaks leak less, of course, and other things that use air can have just a little longer maintenance life out of them. Better on the equipment. Demand. Leaks cost money. Well, I know that. But the basic premise here is that the basic statement is that if I don't remove the air at all, I don't have to pay to replenish it. So just think of it like money in a bank. If you don't spend it, then I won't have to, put it back in the bank. It can be a big deal. Leaks can be 30% of the demand. So I think what you can do is go out into your plant and see if you can't get an idea of how many leaks that you have. And there's actually ways to be helped financially through incentives to fix leaks. More on that on the 30th. Okay, next steps. Locate your compressors. Huh? Oh yeah, where are they? And I don't mean to be facetious, that's true. I mean, a lot of plants, they really don't know where they are because compressors are kind of neglected in the sense that they're just in the background. They're faithfully keeping air pressure in the pipe. And the maintenance operator walks around, does his maintenance. He knows about them, but he's probably not thinking so much about the energy. Of course, maybe if some of those end users and operators are here on this call today, that now you've gained a little bit of appreciation for the energy. But if you're an energy manager or a consultant, you have to go find them. So go to your plant, find your compressors, see if you can't determine what kind of control types it has. And you can get help from the Energy Trust of Oregon, or perhaps even your compressor vendor can help explain what type of controls you have. See where the compressors are set up for pressure. How are they operating? What are they doing? Talk to the compressor operator, so there's somebody there that's faithfully making sure that the compressors are operating and delivering air, because the number one thing is production. No one's ever been fired for having too much compressed air, but if you do not have enough compressed air and production halts, then we're going to start to talk about that. Attend the half-day class on the 30th. And I think there might be food. Is there food? There could be food and coffee, so come. I think there might be some cinnamon rolls or something like that. You might have a lovely door prize. In addition to, if you have a project in mind, contact PG or utility. And you may not right now, but after the half-day class you might. But I think this is a really good opportunity for now to go to your plant and see if you can't think of something that you might be able to do. And you might come up with all kind of, hair-crazed ideas. And they're not necessarily hair-crazed until we talk about them and find out, hey, that's a really good idea. Every class that I teach, somebody comes to me and says, I thought about this harebrained idea, and I thought about it, and I go, nah. And I think about it, and I go, you might be onto something. There might be something we can do here. And they could be very, very good projects. Compressed air is expensive, and there's something we can do about it. First of all, you can receive a free energy consultation. So get a hold of one of these two wonderful people. Paula, I don't believe I've had the pleasure of meeting, but she's wonderful. And John Maloney, of course, is wonderful as well. I have met him. These are great people, so talk about them. They'll help you. And then, of course, is the website up here, portlandgeneral.com/business. So I hope everybody's learned something about compressed air. I think that we are done with the exception of some questions. So, yes.
Thank you, Eric. I assume that you're saying that you're done.
Yeah. I'm done, yeah. There you go. Okay. Always the segue, right? Okay.
All right. Thank you, Eric. I want to thank all of you for joining us today. There's some seminars and webinars here on your screen that are upcoming. Next week we have What's New with EVs and EV charging stations on October the 17th. And as Eric mentioned, October the 30th in Wilsonville we have compressed air systems, and there will be cinnamon rolls and coffee and maybe some fruit. So that would be a good thing for you to come to. Also, electrical safety awareness. I'm only going to mention that one more because there's a list here, but electrical safety awareness is November 6th. And as we have been mentioning safety, thought I would mention that. Now I'd like to proceed to the question and answer portion of the webinar. And actually, before I say question and answer, you can continue to submit questions to me through chat, and we will be mailing you a recording of this webinar and the PDF of the slides shortly. So Eric, the first question we have received is, I can see that variable speed control is more efficient than inlet modulation when a compressor is partly loaded, but I have a fairly new compressor which does not have VFD on it. Can I install a drive on my compressor?
Yeah, excellent question. I like those kind of projects because they're kind of custom. You want to get a good electrical contractor involved that knows variable frequency drives, not just any electrical contractor, but you really need somebody that understands the application. Also, work with your compressor supplier, the manufacturer. You want to find out exactly what this air compressor is capable of. Air compressors, on average, typically can be turned down to about 600 to 900 RPMs. That means that if you have a nominal 1800 RPM direct drive compressor, I can slow it down to about 50%, somewhere between 40 and 50%. That's my turn down. But you always want to ask and work with a professional. Otherwise, you're taking things on your own risk. Now, if it's a 20-year-old compressor, maybe you just go and experiment with it and see what you can do with it. But it's all about the cooling and the oiling. You must maintain good oil and good cooling of the compressor itself. So that's where you're kind of limited. Yeah, good question.
Thanks, Eric. And actually, I neglected to mention that I just opened a survey, a polling survey at the bottom right of your screen. If you could take a few moments to fill that out, we do value your feedback and use it to improve future webinars. So please take a moment to complete that. And next question we have is, most of my plant only requires 80 PSI, but I have one piece of equipment which requires 110. So the whole plant operates at 110. Is there a better way to do this?
Yeah, excellent question. Again, these are kind of custom things. By now, we know that jacking up the pressure is definitely hitting us in the wallet, the pocketbook, in addition to increased leakage. And I'm pumping up the system to 110, all for this little bratty kid over here who's screaming, I need 110, when everybody else is cool with 80. So the option here, a couple options. One might be to just dedicate a smaller compressor to this one device that needs higher compressed air. That might be a way to go. Another option might be to use what's called an air pressure amplifier. And it's a device that you don't plug in the wall. You actually plug into your compressed air system, and it can actually be used to use lower compressed air to generate higher compressed air. That may sound like balls rolling uphill and black magic and all that stuff. We can talk about that more on the 30th, but that might be a really good option. Excellent question.
Thanks, Eric. And so the last question I have, although I do encourage you to submit additional questions, everyone, is our plant manufactures parts which require cooling. Liquid cooling is not acceptable, so we employ compressed air which blows through a 1/4-inch copper tube with crimped ends. Is there anything better you can suggest?
Yeah, boy, the good old quarter-inch copper, tubing that's been crimped. There's a lot of things that aren't good about that. But the number one thing that I see right out of the bat is cooling really just requires wind to blow by it. It really just means, you have on a hot day and you're sweaty and you're wet and you just stand in the wind and it cools you down. You don't need compressed air to do it. You just need movement of the air. So maybe a blower would be a good way to go. The blowers are really nice because they don't pump up to really high pressure only to have it come down to a lower pressure to blow. They only generate what they need, a couple PSI maybe. So that can be a really good option. We can talk about other open blowing options on the 30th. There's some actual special nozzles that you can use. We can talk about that more on the 30th. So hope you come to that to listen. Do we have anything more? One more.
Yep, we have one more question. What about moisture through system?
Yeah, compressed air, moisture in the compressed air system. It's kind of the bane of the system. It's there. There's moisture in the air that we breathe, and when you compress it, it's kind of like a sponge. You compress it down, and then the moisture starts to come out. So there's obviously moisture in the air, and we can never truly remove all of the moisture. So we use things called air dryers to try to remove some of it, and air dryers plug up. Their coolers get fouled. They don't do the proper job, and then we don't remove the moisture that we need to move. So more about air dryers on the 30th, but the basic rule of thumb here is to treat the air to the degree you need, but not more. To dry the air more than what you really need will cost you energy, and they can get very, very expensive. We'll talk about desiccant dryers on the 30th, but you do have to get rid of the moisture. Sometimes you can have point-of-use dryers. If you have a particular application that's particularly sensitive, you can get these little small either desiccant dryers or little refrigerated dryers to treat the air just to one device. Again, not treating the whole system, but only the kid that's screaming, "Hey, I need more dry air," or dry air. Yeah, good question. Definitely opportunities there. Anything more?
Nope, that was our last question, Eric, and I'd like to thank all of you for joining us today. Eric and I will stay online a little bit longer in case you have any additional questions. But again, we'll be sending you an email with the recording of this and the slides. So if you have any questions, please let us know, and we'll hope to see you at a future webinar or seminar. Thank you.